continue our discussion on self bias. Now, we take some design procedure, that is how to know the components, the values of various resistances and voltages and current in the self bias circuit. This comes under design procedure. So, let us consider first the circuit. The simple circuit which we were discussing was this. This was the self bias circuit, and design implies that we should know the value of current I d at the Q point. So, this actually we write as I d Q, and the voltage V d s, and this gate source voltage V G S, and at the Q point this is also to be noted, and this we shall write V G S Q. Q point, the quotient point or operating point, we have to decide, and since mostly these procedures which we are doing, they are going to be adopted to make a amplifying circuit out of MOSFET or junction field effect transistor. So, from the characteristics how we arrive at these values, that we will see, and then we require the value of this resistance R d, R s. About R g we have already talked. R g is there is no current flows through this resistance. So, actually R g, this probe, this gate terminal, this acts as a voltage probe. A voltage probe has to have a very high resistance. So, normally R g is taken 50 kilo ohms or 100 kilo ohms. So, this we say now this is known. These two resistances have to be determined for the circuit, and that will be governed by the drain characteristics. What type of drain characteristics? Drain characteristic tell us the amount of drain currents which flow in the circuit, and what are the various voltages. So, this all comes under design procedure, and we proceed to find out these values. Now, the two equations we arrived earlier by simple summing up of voltages. These equations were V d d equal to V d s plus I d R d plus R s. This was one equation which comes simply when we sum up voltages in the output circuit. Another equation is obtained when we sum up voltages here, and from there came the equation V g s equal to minus I d R s. This can be written in the form I d, the drain current, is equal to minus V g s by R s. This is the equation of a straight line, and when this straight line is plotted on the transconductance curve of the device, that is, this is transconductance curve, and this is the line. When we plot on this, this is like that. This is called bias line, and the slope, its slope of bias line gives the, this depends on the value of R s. So, if we choose R s, that will shift this slope, that means thus baseline will move across this point. So, once we choose the operating point Q, then we know the slope and thus R s is known, and from these curves we also know the value of the drain current at Q point and VGS at Q point. So, three parameters are known. RS, the resistance in the circuit is known, that will be determined by the slope, and slope is dependent on where we choose the operating point. So, normally we choose somewhere in the center, and hence the slope will give the value of RS, and this slope of the line is actually minus 1 by R. So, this will give the value of RS, and at the operating point what is the drain current and what is this voltage. Now, few points we discussed when we were discussing the bipolar transistor and its circuit. Then we will recall from there that these are the DC values, and normally in an amplifier we will use AC signals. So, the variation of current will occur taking this DC value at its center. So, the variations will be, this is the DC value, then AC variations will be along this, and similarly the input voltage is the gate source voltage. So, when we superimpose AC signal on this, then these variations will occur across this Q point value of the gate source voltage. So, this way three parameters are now known: the IDQ, VGS Q and resistance R, all are known. Then the this VGS and this ID, this will give you actually the value of VDS at the Q point also. Let us see the output characteristic, the drain characteristics, they were like this. This is VGS, VDS, ID, and if we choose the operating point, say for example here, then this is IDQ, the same as we got IDQ here. So, that we mark here, and from we extend it and we get VGSQ, IDQ, and this is VDSQ. So, once VDSQ is known, the battery which we use in the circuit, this which is the single DC source in the circuit, normally for the devices, this is the currently used integrated circuits make use of VDD of 5 volts. When discrete devices are used, then this voltage can be high, can be 10 or 12, 15, 30. So, this way VDD is known, and then we use this first equation which we had written, this one, this equation. Here now IDQ is known, RS is known. So, this is known, this is known, and VDSQ is known, VDD, that is the battery source which we are using, that we anyway know. So, this way RD can be calculated. So, this way we find out all the parameters of the circuit. The RD can be calculated from Kirchhoff's voltage law equation for the output circuit. Now, IDQ and DSQ, this is IDQ, this is DSQ, they are taken here from these drain characteristics. There is another procedure which is often employed, and that is, it is the thumb rule that IDQ can be safely taken as IDSS by 2. So, wherever the largest current through the device, this parameter is normally given by the manufacturer. So, once it is known, then it is safest to take IDQ as half of IDSS. Similarly, VDSQ can be taken as 1/3 of VDD or even half of this. So, this way, instead of using these characteristics, IDQ and VSQ can be known from here. So, we have determined all the parameters of this circuit: RD, RS, VDS, ID, VDD and RG, and that is the complete design of the self bias circuit. Self bias is often used for junction field effect transistors, and it can also be used where negative VGS is required in the P MOSFETs particularly. Now, the another biasing circuit is voltage divider bias. It is a broader circuit, and in fact it can be used for getting positive or negative gate source voltage. Both can be, by adjusting proper resistances, this can be used. So, this is having a wider use, and of course, for E MOSFET this is the one which is used. Now, the circuit is this is VDD, this is RD, RS, R1 and R2. Here this voltage VDD is divided, this the network R1, R2, this acts as a voltage divider. So, that is why the name voltage divider bias. Here this is VDS and this is VGS. And this can be used because we can get, this is important, we can get positive or negative VGS. Therefore, it can be used for N and P JFETs or MOSFETs, any kind of MOSFET. This circuit, first we Theveninize it, and the Thevenized, by applying Thevenin's theorem, we Thevenize the circuit, and what we get is this. The Thevenized circuit is this. This is VDD, and this is the resistance we will equivalent, the Thevenin's equivalent of these two resistances. We will tell that how this is determined, and this is the voltage source VG. This is ID, RD, and this is RS. This is Thevenin's equivalent circuit, and here the value of equivalent Thevenin's resistance, equivalent Thevenin resistance. Just to remind you that by applying Thevenin's theorem we can find out this resistance, and for this resistance this DC source is to be grounded. Now and what is the equivalent resistance between these 2 points, between this and ground? So that is to be determined. Now once we ground this terminal also, then this is like this. This is R1, this is R2. So as far as this point is concerned, this Thevenin's resistance this is equal to the parallel combination of these two resistances, which is Rg is simply R1 R2 by R1 plus R2. This is Thevenin's equivalent resistance. The voltage is, what is the voltage which this VDD produces between gate and source? So the equivalent circuit actually will be this. This is VDD, and this is the two resistances. This is R1, this is R2, and here we have to find out this is VG. So obviously the DC current through this circuit is, the current is VDD by R1 plus R2, and the voltage drop across R2, voltage drop across R2 is simply, that is VG. VG is simply R2 VDD, this current into this resistance. So R2 into this current, so R1 plus R2. This is VG. Now once this is there, this current we take as Ig, and we apply the summation of voltages, that is Kirchhoff's voltage law in the gate source circuit of this. So, applying Kirchhoff's voltage law at gate source circuit of Thevenin equivalent circuit, we get the equation VGS plus ID RS minus Vg plus Ig Rg is equal to 0. Here this is VGS. So, we start with, we are finding out the summation of voltages, we are writing the equation for summation of voltages in this circuit. So, VGS, then ID into RS, then minus Vg plus Ig and Rg equal to 0, where this Vg is given by this expression and Ig here is 0, since why Ig is 0? Because all gates are operated in reverse bias. So, Ig is 0, and then we get from here when we put, so this term goes and we simply get VGS is equal to Vg minus ID Rs. This is the fundamental equation, and this clearly shows that VGS, the gate source voltage, can be obtained either negative or positive. If it is to be positive, then Vg must be greater than ID Rs. The drop across this resistance should be smaller than Vg, that will give positive value of VGS. Or if negative value is desired, then the drop across resistance Rs has to be higher than Vg. So, this is actually, this is the equation of load line, or we call it bias line. And this is to be plotted on the transfer characteristics of the device to find various important parameters. So, when we plot this here, these are the characteristics. This is VGS, ID, the output current, and input voltage. Input voltage is gate source voltage, and this is the equation of a straight line. From here, at this point, VGS is 0. When VGS is 0, then current ID from here we will get ID equal to Vg by Rs. This is the point, and to get this point here ID is 0. So, this is the point which gives the value of Vg, and where this load line cuts the transfer characteristics, this is the Q point. Q point. And now we will proceed to find out, for example, what is how to get negative and positive voltages. First, let us take for NMOS on N MOSFET where VGS is positive. And for positive, from this equation, baseline equation, load line equation, Vg has to be greater than IDRS. We substitute here the value of VG. The value of Vg is here in this equation. So, this we substitute here and let us see what we get. So, when we substitute the value, we get R2 VDD by R1 plus R2. This should be greater than IDRS, or VDD by 1 plus R1 by R2 should be greater than IDRS. This inequality can be satisfied obviously if RS is chosen very large. If R2 is chosen very large, then this inequality can be easily satisfied. In the limiting case, R2 in this circuit, in the voltage divider circuit, R2 can be taken as infinity, almost approaching infinity, and in fact it can be taken as infinity approaching R infinity. And what is R infinity? The absence of the resistance. If R2 is removed from the circuit, then we satisfy this inequality easily. So, the circuit is reduced to this, we remove from here R2, so that the circuit is this is NMOS, this is RS, and this is R1, this is VDD, and this is RD. Here we will observe VG. This is the circuit, biasing circuit, just one resistance here instead of in the self bias the resistance was here. So, we can bias, we can get a positive gate source voltage which is required, for example, for NMOS. Here this is NMOS. And if we intend to get a negative voltage, when negative gate source voltage is required, negative VGS is required. For example, for biasing a N JFET or PMOS, then Vg has to be smaller than IDRS. And when we substitute for Vg, we get is less than IDRS or VDD 1 plus R1 R2. This has to be less than IDRS. This inequality can be satisfied if R1 is very large. If R1 is made very large, and in the limiting case R1 can be infinitely high. That means if we remove R1, then we will get a negative gate source voltage, and the circuit will be the same as we have got for self bias. That is, this circuit will be reduced voltage divider bias. If we remove this resistance R1 here to make it infinity, that will reduce this circuit to this form. Where this is VDD, RD, RS, and these voltage, this is of course VDS, this is VGS, and this is R2, which is same as we have taken earlier RG. So, this is the circuit to get a negative gate source voltage from the voltage divider bias, and we can get the positive also, as we have seen in the previous case. So, this way this voltage divider bias can be used, and this is the one which is quite widely used with the MOS devices, and thus we finish the biasing of the FETs and MOSFETs. Any kind of FET, junction field effect transistor, or MOSFET can be biased by using these two biasing networks. The next thing which we are going to have, that is small signal F parameters. Small signal FET or MOSFET parameters. This we are going to study now. For BJT, we have seen that beta, the current gain, beta for bipolar junction transistor BJT was most popular, and this was the ratio of output current to input current. This parameter beta appeared in the expressions for input impedance Zin or voltage gain and so on. Field effect transistor or MOSFETs, they are voltage operative device. Here the important parameter is transconductance. Transconductance of the device, which is written as GM. So, GM, transconductance parameter, is most important parameter for a junction field effect transistor or for MOSFET. And first we will define it, and then we will go for other small signal parameter. So, transconductance GM. This is defined as, because we will be concerned with the AC operation of the device. So, we can define the AC drain current by AC. So, when on the Q point, when we superimpose the signal, what is ID and VGS, the ratio of the two, which can be shown equal to, let us see, for first for a FET, the JFET, here this is the transconductance curve, and this is Vp, and this is ID, this is VGS. So, this curve is the transconductance curve, and at the operating point we draw a small tangent and we find out this is change in the drain current ID, and this is the change in gate voltage. So, this ratio can be written as change in ID by change in VGS at constant VDS. This is the way it is defined. Now, this is obvious that if we choose Q point here, 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 then everywhere GM is changing, and GM is highest near this IDDS, short circuit drain source current, when gate is shorted to source. This is the highest value and the slope is highest here. So, here this GM will have highest value. The highest value of GM is designated as GMO. This is the highest value of GM, which is actually the transconductance value near IDSS point on the transconductance curve. Now, GMO can be determined, as we are seeing from the transconductance curve here, by taking this operating point in the vicinity of IDSS, or it is GMO can also be obtained from the simple relation GMO is equal to 2 IDSS by Vp. From here also GMO can be obtained. Now, once GMO is known either from that graph directly or by using these two parameters, then we require transconductance value at the operating point. And as I said, because the slope is changing, so GM is changing quite a bit along the transconductance curve. So, for accurate analysis, at the Q point the value of Gm, the transconductance is required. And so from GMO, the maximum value which is either provided by the manufacturer or can be obtained from the data provided by the manufacturer, we can find Gm for any value of VGS depending on our Q point, we can get from here. This is the equation which can be used to get value of transconductance parameter from GMO by substituting the value of at what gate source voltage we require this value. We can get from here, where here this is the pinch off voltage. This example we took for this graph we took for a JFET. For a MOSFET, the curve will be like this. And here we choose the operating point and we drop. So, the same thing, we get the value of ID, change in ID, and this is the change in VGS. The ratio will give GM for a MOSFET at the Q point. The another small signal parameter which we require, and that is the small signal output resistance. This is defined as, it is written as either RD or as RDS. This is actually the resistance of the channel in the circuit, and this is defined as this is defined as RDS is equal to output voltage by output current. That is VDS, AC value of the drain source voltage and the AC drain current, which is same as changes in VDS by changes in the drain current at, this is constant VGS constant. This is actually, if we look at the drain characteristics, this was ID and this is VDS, then this resistance represents this slope of the drain characteristics in the saturation region, which is nearly horizontal, and that states that RDS is very large, very high, and for JFET RDS or simply RD, this is 50 coulombs to several hundred kilo ohms. And for MOSFETs, RDS is up to 100 kilo ohm. Actually, when we take the circuit actual analysis, we will see that normally smaller resistances will be put in parallel with this RDS. So, RDS effect that way will be negligibly small. So, these two most important parameters we discussed. One was transconductance, which will appear, for example, we want to know what is the voltage gain of a MOSFET amplifier. Then there essentially one of the parameters which will appear is transconductance parameter. And then we discussed about the small signal output resistance of the device, and that is normally very high for JFET or for MOSFET. The next thing which we take, that is a small signal FET model. A small signal FET and also the same model for MOSFET. When we were discussing the bipolar transistor and its model, we have already seen the utility. In a circuit, when the device is replaced by its model, that enables the analysis by using simple algebraic equation, summation of voltages etc. or currents. We can find the value of output voltage versus input voltage, which will be the voltage gain. Similarly, if input impedance is to be determined or any other parameter is to be determined, then a small signal model is very useful. So, we are now developing a small signal model for FET, which is also applicable for MOSFETs. Now, any two conductors when separated with a dielectric insulator, there is a capacitance associated. So, when we talk of the exact model of the device, because there are several conducting paths in the device, there will be capacitances. For example, between gate and source there will be a capacitance. Similarly, between gate and drain there will be a capacitance. So, if we talk of the exact model, which we will simplify, of course, we will have to take into account these capacitances and all kinds of resistances. So, the model for the device will be this. This is the gate terminal here, and this hole is source, and here is drain. this is that output is resistance which we talked, RDS, and this is the current source, and this is GM into VGS, and this is the capacitance between gate and drain, and this is the capacitance between gate and source, and this is the resistance between gate and source. This is the exact model, but we can simplify. For example, we are talking of moderate frequencies, and these frequencies will be normally up to few tens of kilohertz. There, these impedances offered by these two capacitances, they are very high, and very high impedances becomes almost they can be taken out from the circuit. So, we can drop capacitances CGS and CGD. These capacitances we can drop for the frequencies which are presently under discussion. Also, this resistance between gate and source is very high. For JFET, this is hundreds of kilo ohms. RGS for JFET, this is several hundred kilo ohms, and for MOSFETs at least 2 orders of magnitude higher. So, this resistance can be also taken out. Then what we are left is this model. This is gate terminal, this is source, and this is drain, and this is RDS, and this is the current source. This has the dimensions of the current source, because GM we know, GM is ID versus VGS. So, GM into VGS is equal to ID. So, this is the current source and here, and this current source is the magnitude of this current is dependent on the gate source voltage, whatever voltage we apply here, VGS. So, this is the model which we will be using, and remember it is very simple model. This is one resistance which we will see when we put actual resistance here, then the two resistances in parallel, one very high resistance, one low resistance, then the effective resistance of the parallel combination will be closer to the smaller resistance. So, this will also disappear, and so the current source remains, and this we are going to use for the analysis of FET amplifiers. We are going to study 3 amplifiers: the common source amplifier, the common drain amplifier and common gate amplifier. Like BJT can be used in 3 different configurations, so is the case with FET. This can also be used for 3 different configurations. So, we will derive the useful parameters for all these amplifiers using this model, and we will see that we will come to a net conclusion that like common emitter amplifier in BJT, common source amplifier with MOSFETs and with the FETs is most widely used, and we will be studying that.